Seems to be working. Okay. What they have to put up the title? The title is the troublesome reflection rule. Okay, so I'm going to speak about what goes wrong with type theory from an implementation point of view when you add the reflection rule to it. So let me first just recall what sort of type theory, what are the basic building blocks of type theory, and I'm going to use a very simple type theory, which will only have products and equality types and nothing else. So in a way, it looks a bit like a logical framework with broken equation equality, but we'll come to that. Okay, so we're going to have a type theory, dependent type theory, of course. So what are the basic judgments? The basic judgments, which I'm not going to write down here in all gory detail. If you want to know, you can ask. That something is a context. So context is typically looks like this. And each variable, the type of each variable may depend on all the previous ones. And then we have the basic judgments in a context, namely that something is a type, but I'm going to, just for the purposes of the talk, I'm going to simplify things, and I'm going to assume that there is a type which is in type. This makes a type system inconsistent in the sense that every type is inhabited, but later on we can think about, something like a la Coq, having a hierarchy of universes and so on. But I don't want to get into these questions right now because they're mostly orthogonal to what I will discuss. So then we have that a term has a given type, and then we have equations. And so the equations are, there's an equation that A equals B at some type A. And I don't need equality of types if I assume type in type, because then equality of two types is just equality at type. But you could separate these, and it's customary to separate them, so that equality of types is a different judgment than equality of terms. Okay, so these are the building blocks. Now the only types that I'm going to have are products, pi, and no surprises come here. So you say, well, there is a formation rule, so the formation rule is something like this. If in the context where X has type A, B is a type, then in this context, by XA, however you write this, B is a type. Then we have the introduction form, which is lambda abstraction, and I'm not going to write down the rule, unless you force me to. Lambda abstraction, then there is application. So you'd write this as lambda XA E, and application E1 applied to E2 with the expected rules. And then there are equations governing this, which are the beta, and I also generally want to consider the eta rules. Okay, so products with betas. And then there's an equality type. And I'll write this one like this. It's called EC A, B. And this one, let me be a bit more careful about this one. This one goes as follows. If I have in a context gamma, A is a type, and A has type A, and B has type A, then I may form the type EC AB, which is a type. If in a context gamma A has type A, then I can form, this is the introduction form, the reflection term, refl A, and it has type ek A. So that's the reflection rule. There is no eliminator because we don't need it and there is nothing. This is not the troublesome reflection rule, this is the reflexivity term. Yes, there is no eliminator because you don't need it. But instead you have the troublesome reflection rule, and the troublesome reflection rule says this. If you can build a term of type ek AB, then A equals B. This was part of the original Martin-Löf type theory, this rule. But it destroys very many nice properties of the type system, and we are going to look at how and what gets destroyed a little bit. Let's see what are some initial observations I want to make. Yes, so first of all, once we have this rule, we can recover the expected eliminator. So we can recover an elimination rule. There is an eliminator for the identity types, which is the J, and you can get it from this. Do I have to do this? Maybe I can try to do the simplified variant. So you would expect that something like this holds. Let me see. Just the simple one, because the complicated one is, I can't possibly get it right. Okay, so the simple one would be like this. Suppose you have a type family. Oh, so a type family is just going to be for me a function from a type, from A to type. I can do this because I'm using the type in type hack. I'll just think of them like this. So if I have a type family P, and then I have an element A in A, and I have an element B in A, and I have, let's see, which one do I want? I have P, which tells me that A and B are equal. And then I can get some U in P of little a. So here's the picture. Here's A, here's little a, here's little b. These two are equal. Then up here I have P of little a, and inside of it I have U. Then up here I have P of B. And now the simple eliminator tells us that I can take this U, transport it over, and I get something here. And this could be written in a semi-sloppy way as transport. Well, let's not do it in a sloppy way. I would want from this data, I want to do what? I want to get something that I might call transport along P of, and I say, using the path P from A to B, you can transport U to land in P of B. Yes? So how do I do this? Well, I just use the reflection rule, and then I use some other general rules which I haven't told you about. Now, the general rules are the ones that explain what this equality is about. That this equality is about substitution. It says that I can substitute equals for equals. So there would have to be rules like that, which I haven't mentioned, which essentially say if you see A, you can replace it with B if A and B are equal. So here, I use reflection here. How does this go? Use reflection to conclude that A equals B. And then, with a little bit of care, what you can do? Well, I can just say, well, then I can replace this A by B. So therefore, because A equals B, P of A equals P of B by some other general rules. And then because P of A equals B, by substitution, if I have U in P of A, I get, so there's then yet another general rule which says that equal types can be substituted. So because I already have U is in P of A, these two together will give me that U is in P of B. And so this simply is my transport. This is what we were looking for. It's this one. This is that. So you see that you will get a very, very strong eliminator. So essentially doesn't do anything. Okay. So that sounds nice. It's a little weird because this is the first sign that things are not quite what they're supposed to be, because I have a type and I have an introduction form for it and I have no eliminator, and then I get eliminator by magic or by dirty tricks or however you want to understand this. So this is already saying this, if you do a lot of, well, even if you don't do a lot of type theory, if you do some amount of type theory, this looks odd and suspicious. Okay, so what are some other horrible things that come with this rule? Okay, so first, so one would be something like this. So exchange is not valid. So what is the exchange rule? The exchange rule says that if I have a context gamma, and in it I have x of type A and y of type B, and then there's some further context, if this is a valid context, and if, let's see what, if x is not free in B, and possibly, so y cannot appear in A by assumption, because this is a context, it means gamma does not contain y, therefore A does not contain y, so I don't have to worry about that. So if this is a context and B does not depend on X, then I can move X over. Then this is also going to be a valid context. Okay? But once you have the reflection rule, it may happen that you have here an assumption which allows you to build the type B without mentioning this assumption, because it will never appear. So let me give an explicit example of how this works. I will actually set up a general example that works, and then you will see quickly how this leads to trouble. Okay, so to set things up, you can do the following. So I will show you how to assume that any two types are equal. Okay, so take any types, let's call them X and Y, define a type family, assuming we have booleans. Okay, so we'll need booleans, but no, actually, let me do just the exchange rule here. Stay with the exchange rule. Okay, so I could have gamma empty and delta empty, and then this will be the trouble here. Okay, so I will say assume that. We need a little more than that. Okay, so let's see. Assume that we have two types. So assume that we have types X and Y. Then assume that little x is in X. Then assume, let's see, which one do I need? Little y is in Y. Assume that X and Y are equal types. Okay, so actually this is my gamma, I think. Up to here is gamma. And now I say assume that X equals Y. So little x equals Y. Okay? So now, is this a valid context? Yes, this is a valid context. So up to here, there is no trouble. Here, you look at this and you say, well, how can this be? For this to be the case, x has to have type x. Okay, yes, it does. It's okay. And y has to have type x, but it doesn't. Y has type y. However, by using reflection and p, I see that x and y are equal types. Therefore, this is okay. But now, if I switch these two over, p and q, then when I have to show that this is a well-formed type, I don't have p at my disposal. And because I don't have p at my disposal, I cannot show that this is a well-formed type. So exchange is not valid. I can exchange two things. See, crucially, p, of course, is not appearing in here. There's no p in here. So I cannot do exchange. Next, strengthening is invalid. Strengthening says the following. Ooh, I can use fancy technology. So, strengthening is invalid. Strengthening says the following thing. If you have gamma x type A, delta, and then you show that B has type B. And in fact, x is not used, which means x is not a free variable in delta, and it's not a free variable in the B's. So it does not appear here, it does not appear here, and it does not appear here. It's never used. Okay? You want from this to follow then then you want the following to be derivable as well. You just throw away x. Okay? So now let's think a little bit about when this might be valid. First of all, if I can come up with an inhabitant of type A, if I can actually find a term of type A, then I can substitute it everywhere for x, and I would be okay. So this would be a non-problematic case. A problematic case is when A might be potentially empty, and then this looks very suspicious. However, you can show that if you have a nice enough type theory, this is valid anyhow. So for example, in Coq, it's valid. So in Coq, you can delete a variable if it's not used in the middle of the proof. It's an admissible thing. That is to say, the way you imagine this is, suppose you have a derivation of this b, little b, you have a derivation up here, and you have to somehow see that whenever x got used, it got used in some inessential way that you could eliminate. Okay, so it's not going to be a simple property, but it's there. And so this doesn't hold anymore. And the reason why it doesn't hold is precisely the same as before. Here I cannot delete p, right? It's never used, it's never mentioned, but I cannot delete it. Okay? Okay, so let me show you another nasty example. Now that I wrote this, I have to probably continue like that. Okay. Yes. So suppose we have an assumption P. Let's suppose we have some types now, just to be able to speak about concrete types. Suppose we have natural numbers and booleans, axiomatized in some reasonable way. And so suppose we assume that nat arrow nat equals bool, nat arrow bool. By the way, you may think, well, you're assuming the two types are equal. Once we have a hierarchy of types, maybe you have to assume that the names are equal and so on. Or if you don't have type, maybe you can't assume this. There will always be a way of effectively assuming the two types are equal, because I can just assume that false equals true, and then have a type family where false maps to one type and true to another type. So this is an inescapable assumption that I will be able to reproduce it even if you tweak my type system a little bit. If you leave the reflection rule in, then something like this follows. Okay, so first of all, you might ask, how unreasonable is it to assume that nat arrow nat equals nat arrow bool? it's not entirely unreasonable. For instance, in set theory, these two sets would be isomorphic. And they would also be isomorphic in other places, like in the effective topos. They are isomorphic. So they might be isomorphic, and so maybe I can actually have a denotational semantics where, as a special case, I make sure that net arrow net equals net arrow bool. So it's not completely unreasonable to say that this assumption by itself is not, it's unusual, but I know that just by itself, this assumption is not going to be contradictory. So now with this, I can then form something like this. For example, I can form this type. Lambda x nat false applied to 5 and maybe all of this plus 7. Okay, this is going to be well typed and it has the type nat because this thing here has type net arrow bool, but net arrow bool is the same thing as net arrow nat by reflection and using assumption P, and so this is well typed and so everything looks okay. However, if I beta reduce this thing, then here I get false. So the beta reduction of this is false plus 7, and this is not well typed. This would be well typed if I knew that bool equals nat, but I don't know that bool equals nat. I know that net arrow nat equals net arrow bool, and I cannot derive from this that nat equals bool. So beta reduction has to be done much more carefully than it usually is. So there's something's wrong here, and you need to figure out what's wrong here, because you have to be able to detect that this is not a valid reduction. Also, in nice type theories, if in a nice type theory, if you know that x arrow y equals u arrow v, then you will know that x equals u and y equals v. Type constructors are injective in nice type theories and not so here. So here you cannot assume that, well, we discussed this with Chris Stone. If you assume injectivity of type constructors, then once you assume that net arrow nat equals net arrow bool, you will also know that nat equals bool, and then this will be well typed. But it seemed that, at least for the kinds of models that Vladimir Voevodsky was thinking about, he definitely doesn't want injectivity of constructors. So, for instance, in set theory, it could easily happen that you have something like this. Empty cross A is actually the empty set. Well, but then empty cross B is actually the empty set, but this doesn't mean that A and B are the same set. So this would be an example where you have a natural semantics with non-injective type constructors. And so maybe we don't want to assume this, so in general I don't want to assume this sort of thing. So that means that, you see, there are two ways you could try to fix this beta. You can try fixing it by prohibiting it, so you have to be able to detect that this is not a valid beta reduction. That's one possibility. The other possibility is you come up with reasons why this beta is a valid reduction, in which case you will be highly tempted to say something like, oh, maybe I have injective type constructors, therefore nat equals bool, so everything is okay here. But I don't want to go down that road. It seems much more reasonable to make sure that such beta reductions don't happen. So there's going to be a price to pay. We need to pay a price for this, by the way. We need the term. If I stare at this term, I can't tell. It's too late with the information given. If I just stare at this term, it's impossible to tell whether I can beta reduce or not. The term must contain extra information so that I know whether I can beta reduce. So in particular, what we need is when we have applications, we need to record the type of the application, and we need to record the codomain of the lambda abstraction. So you need a lot more typing annotations to be able to fix these things. If you can optimize the typing annotations, I'd be very glad to know how. We have optimized them some because they are the main source of inefficiency in an implementation. There's lots of type annotations everywhere. Okay, so I'll try not to go on forever. So this hopefully gives you some idea of how bad things are. Okay, so the bad. You can't do the structural things which are usually true for contexts are not true. And then you have to be very careful about betas and so on. So now, what to do? First of all, if we're thinking about some sort of a proof assistant or something that will check formal terms, a program that will check things, then the first thing we need to do is we need to present the type theory in some reasonable way. That is to say, we need to have it in a more algorithmic, we need to express it in an algorithmic way. Because the way classically type theory, if you look at classical, I don't want to say classical type theory. If you look at type theory as usually formulated, it contains typing judgments and equations. So in essence, you should think of it as an equational theory. It says there's stuff you can build. That's like saying, well, in a group you have an operation and you can use it to create elements of the group. In type theory, you have term constructors and eliminators, and you can use them to create stuff. And then some of that stuff is equal to some other stuff. Yes? That's essentially what type theory is. So in this sense, it reminds one more of algebra than anything else. It's not, I don't think of it as a programming language because there is nothing there that tells you in what sense it's a programming language. It's only a programming language after you have done some work. So the work you need to do is you need to reformulate the usual rules of type theory in a more let me call it computational way. Of course, this has been done by many people before. Various things have been invented and ways of doing this. So one that I think maybe just to give you a feeling for what this means, let me describe one of them. Okay, so type-directed. If you have a bidirectional type theory with type-directed equality. Okay, so you need to do things like this. First, so what happens in general is instead of having just 4 forms of judgment, well, actually we have just 2 forms of judgment. A term has a type, and 2 terms are equal. Instead of that, we're going to have a lot more kinds of judgments, and there will be specialized judgments. And when you have a judgment, you will think of it as sometimes you will think of it as a function which has some inputs and some outputs. And then we're going to write down our rules so that we can actually see how to compute the inputs and the outputs. So you would type this stuff into Prolog. If Prolog were, cannot be quite Prolog, but almost Prolog, it will just do the thing. Okay. So for example, what you do is instead of having gamma, I'm not going to describe the whole thing. I'm just trying to set up the correct mode of thinking as to what sort of thing we're doing here. So instead of saying A has type A, this typically, one way to do this is you split it up and you say, well, when you have a term, sometimes you can tell what its type is. So if I give you a term, like for example this one up here, where is it? This one up here, you can tell that it's nat to bool. You don't have to be told that it's nat to bool. Yes? But sometimes you can't tell what it is, but you could check. If somebody told you the type, you could check whether it's that type. So you split this into 2. One, so some people write the up and down arrow, but I can never remember which one is which. So I write left and right. So this becomes this and that. So this means infer type of A. So in this case, you would say that this is input and that's output. I'm telling you should imagine it that way, but I'm not defining anything. This is helpful suggestion. Okay? And then when I write the rules, you have to see that I wrote the rules in such a way that you could just transcribe them into ML or Haskell, and that's what you do. And here they're both input. So the type checking, this means check. So here you say check that A has type A. And this either succeeds or it fails. And if it fails, that means something's gone wrong. Okay? So the output is determination. If it comes back, it means it succeeded. So this has been split into two. Now you split then you split things in further. Equations get split, and with equations you say, well, how are we going to check an equation? And it turns out that a very cool way of checking whether an equation holds, so having something like this. Oh, by the way, when you do this, it turns out that there is exactly one rule which mentions equations, and it's this rule. It says, there are further tricks I'm not explaining here, but there is one rule which says, in order to check that A has type A, for certain kinds of terms here, I'm not explaining everything, but there is a rule of this form, and it's the only one that employs equality. What you can do is, you can infer the type of A, and you're going to get some type B, and then you check that they're equal. You can arrange things so that this appears only here in these rules. Okay? So that's also kind of cool, because then you're exactly controlling where equality will be used. Because the rules of equality the rules for equality are such that you could use them anywhere. This is not useful. Algorithmically, you cannot keep asking yourself whether you should be using an equality rule. It has to be directed. So then you're faced with the question, how do I see whether the two types or two terms in general are equal? And what you do is you look at how this might work. And one cool way of doing this is that you have two phases. You have a type-directed phase in which you don't look at the terms, but you look at the type. And the type tells you how to make progress. So a typical example would be, suppose I am comparing A equals B and my type is of the form C cross D. Well, how could I do this? Well, I could do this by comparing the first component of A to the first component of B at type C, and then I compare the second component of A to the second component of B at type D. Yes? You see that I have a good criterion on when to use this rule. I use this rule if my type is a Cartesian product. I don't care what A and B are. I will use it when the type is a Cartesian product. So other type constructors are of this form, and these are generally the eta rules. The eta rules tell you how to make the type at which we are comparing smaller. So you first apply your eta rules to make your type smaller. You eventually arrive at a primitive type or some type variable where you don't know what to do. Once you don't know what to do, then you enter the second phase. So this is the type-directed phase. And then that's the normalization phase. Then you start using beta rules so that you compute. So we have here type-directed. You make the type at which you're comparing smaller, and in general, this will be the eta rules. Then you have the normalization phase. You end up with two terms and some type, and you have no idea what to do with this type, because maybe it's a variable, okay? Or maybe it's a type family. It's like you have this X. Maybe it's even applied to something. It's a dependent type, but you don't know which dependent type. It's just schematic. So now, the only chance you have to discover whether A and B are equal is to actually make them syntactically equal. If I make them syntactically equal, then I win. Then I know that they're the same. So what you do is you compute this one, and you compute that one, to get some other form, and then you hope that this form is better. Yes? And this compute means, more or less, you use beta rules until you expose a constructor. So until both terms have a constructor on the outside. So for example, they're both ordered pairs, or they're both cons for a list, or they're both successor, or one is the successor, the other one is some other constructor, 0, right? But you want them both to be constructor on the outside. Well, if that's the case, then I compare the constructors. If they're the same, I continue. If they're not the same, I say this is what is this is not equal. So and then I continue with the subterms. So I use this lazily, compute lazily, just so that I can get lazily, so that I get the outer constructors out of them. So this would be is what's normally known as weak head normal form. And when this phase is going on, here the type doesn't change. Here the type is always the same. It's x, it's still x. But then things get subdivided into subterms, and so maybe I start comparing some other things, because I start comparing subterms of this one to subterms of that one. I get new subterms, and these guys now have new types, and there is no guarantee. These types could be arbitrarily complex, so the whole thing begins again. Okay, so now I go back and I start over. Okay, so this is one way to you organize your type theory so that everything is an algorithm, because I use the shape of the term to tell me whether I should be, I use the syntactic form of the term to tell whether I should be checking or synthesizing it, so inferring or checking, yes. And then once I get to equality, I use this type directly thing. So that's a typical way of organizing type theory. Now, a real proof assistant does a lot more on top. For example, typically a real proof assistant is not going to be like this. It will, at the very least, have missing arguments. There's something called implicit arguments, where you leave out arguments, and then the proof assistant is supposed to figure out what they were. This is an extremely useful thing, and if you don't have it, it's very difficult to use the proof assistant. That's a different kind of problem we have, which we haven't attacked here. So what we are aiming for is a sort of algorithmic base on how to deal with type theory, which is possibly very nasty. So one that has reflection rule. So a type theory with reflection rule, which is very nasty, but we want to have some sort of an algorithmic base. Now, because I know in advance that my type theory has undecidable type checking, which means I cannot possibly have a terminating algorithm that will tell me whether a given thing has a given type, I shouldn't be aiming for the impossible. So what should I be aiming for? I want to aim for, so I want to view the whole project as a programming language design problem. So I'm a person with a program, I have a hammer, everything's a nail. My hammer is the programming language theory, and I see programming languages everywhere, so I see them here. Okay, so I want to have a programming language, you can think of it as a programming language, which will allow me to do certain things. So I want to have a programming language. Oops. Which is, first of all, it has to be sound, which means cannot derive things unless they're derivable. So if my language computes something, if when I run the thing and it says, yep, everything is okay, that means everything is okay. Okay. Yes. Okay, so, but maybe my language is of the kind where it never comes back. Maybe something is actually derivable, but it will never discover that it's derivable. Or maybe, so that would be, I'm going to mention the next possible desirable thing, which would be completeness. Completeness would mean anything that is derivable, I can actually write a program that derives it. Okay. Soundness is an absolute requirement. Without soundness, I don't think we're doing anything useful. Completeness is desirable, but I don't want to worry about it right now. Okay? And then, of course, this is a programming language exercise. The thing that really matters, actually, that matters most to most programmers in practice is expressivity. Right? Older programming languages typically sacrifice soundness for expressivity or efficiency. Down the list, there is efficiency. Yes? So these are typical design issues. These are the constraints that determine our space of designs. Okay. So, what to do? The view that I think, so we've been thinking, Chris Stone and Mattia Prittner and I have been thinking about this on and off now for a while. And the way I want to view this is as follows. When you have a judgment, suppose you have a judgment, you have derived something. Then suppose this judgment has a derivation. Up here is some huge tree that it has a derivation. In nice type theories, you have the following property. If somebody gives you the bottom line, then you can tell whether there is something up here. Yes? And in fact, you have an algorithm that goes and finds it. This, there is no hope of. There's no hope for, we cannot possibly have that. We know in advance. But we still, what can a programming language do? Well, you see, some parts of the derivation here are going to be of this form. Somewhere in the middle of the derivation, you will show the two things are equal. And then this part of the, and you will do this by reflection. And so what's up here, this gets lost. It's not down in A anymore. You have worked hard to produce your P, to figure out that X and Y are equal, then you throw it away. And because you throw it away here, because you don't have this thing, that means it gets really difficult for you to reconstruct the derivation, or any derivation. You would be happy with some other derivation. But certainly, if there was a given derivation, and you threw out parts of the tree, and they don't appear, they're not recorded down here anymore, and there's no easy way to reconstruct them, because sometimes there is an easy way to reconstruct them, or you can sometimes reconstruct something that's equivalent to whatever was lost, but in these cases, it's not. It's really gone. So one gets the idea that somehow the P must be provided, right? You want to provide P, and then you have to say, well, if I want to provide the extra information, it's not going to be just one P. Maybe there's going to be a Q up here that also is necessary, and we don't know how to get it. So there will be pieces of the tree that are missing. It would be good if the missing pieces are only equations. If I'm missing whole terms, so derivations of terms, that's a little worse than just missing pieces which explain why things are equal. So I would like to separate things here into what I would call the proof relevant and the proof irrelevant parts. And the proof irrelevant parts are essentially the equations. But maybe in the future time there will be a more general technique for what I'm doing here, where I will say, well, in general, when you have a type system, some pieces of the type system are what you would call proof relevant because they get, those are the parts of the derivation that get recorded in the term. You can tell the trace is left in the term. And then there are some other parts of the derivation which are proof irrelevant. That means that's something you had to do, but then you forgot how you did it, and you just remember the memory that you did it. Okay? So in fact, that's something that happens all the time, also in existing proof assistants, of course, and they throw away the information. Every time a proof assistant checks the two types are equal, that's exactly what it does. It calculates to its satisfaction the two types are equal. So implicitly, it builds such a derivation, except that this derivation is not stored in memory anywhere. It's stored in time. It's in the execution trace of the algorithm. The fact that the algorithm finished and said, okay, is the derivation in a proof assistant. Why aren't we storing it? Because it's very expensive, it's useless, and we can reconstruct it anyway. But now we are in a situation where we will not be able to reconstruct it. Okay? So that's the scene. Okay, so I would say, I would try something like this. Okay, I'll try something as follows. I would try this algorithm which I have here, the algorithmic reformulation of type theory, which says, well, you have the type inference and type checking phases, and they're connected by an equality check. Okay? I would try to keep these two the same, so that more or less the algorithm is still driven by inference and checking. But then, when you get to this question of why are two things equal, then you have to stop and do something different. Okay? You cannot run this algorithm. If you run this normalization algorithm, oh, by the way, if you run the normalization algorithm, things can go horribly wrong. So maybe just as a remark, I can, of course, have an assumption that there is a type D which equals D arrow D. And once I have such an assumption, I can well type non-normalizing terms. I can well type lambda x xx. So lambda xd, lambda xd, xx is well typed. And this is the road to hell now, right? Because you just do the usual thing and get yourself a loop. So any kind of normalization like that has to be, there has to be something, we have to be aware that normalization doesn't terminate anymore. Weak head normal forms do not necessarily exist. So there's that, okay? So the question is what to do with the equations. And here's where we come to the question of computational effects. Okay, so what would be some reasonable ways for people to provide this extra information that's missing? So I'm going to have a typing derivation which is doing its type checking and type inference, and there are these pieces of the derivation which are nice, and the algorithm is running, and then it says, now I want to know the two things are equal. Okay, so you could try to store the information that two things are equal somewhere in the term. So one idea is that the missing pieces, Q and P, somehow have to be provided anyway in this A, or maybe in the type, or somewhere, somehow. So the idea is annotate A and maybe A with missing terms of type X. Yeah. This, well, if I just give you a bunch of missing terms and I don't tell you where to use them, that's going to be pretty useless. So for example, if I just, provide the list here, then maybe that's enough for you to do something, but it's probably not very efficient. Oh, by the way, you can always do the following silly thing. Whenever you're faced with a missing derivation here, you can enumerate all possible derivations and see if one of them works. This is a possibly non-terminating procedure, but if there is one, it will terminate. So theoretically speaking, what we have here is derivability is not decidable anymore, it's semi-decidable. So I don't really consider that to be a very useful thing. But it tells you what to do. Okay, so semi-decidability means I look for a witness and maybe one day I will find one. Okay? Well, there is the projection theorem which says anything that's semi-decidable is the projection of something that's decidable. That is to say, instead of saying I will look for a witness, I can instead say if somebody gives me a witness, I can check whether it's okay. Yes? And so this is what this missing stuff is about. Maybe the missing witnesses, the missing information is the witnesses, is the annotations. You can think of them as witnesses. What form should the witnesses take? Okay, so annotations. If they're just sitting there and I'm not told when and how to use them, that's likely to be useless. I don't see, it's not necessarily a good idea. So they need to not just tell me, you need to tell me not just what they are, but also where in the derivation will I need them. But this gets very nasty because I don't have the derivation, yet I have to tell you where in the derivation I will need them. I have to somehow direct this, right? I have to say, you will need P and Q, and by the way, you will need Q when you get to some checking of some subterm that arose during normalization. This term does not even appear in your original term. That's very important. Yes? So I may have terms which do not appear in the original term. Subterms that have been normalizing for a while and now they look different from what I started with. And that's where I need my missing information. So this is not just about providing what's missing, but also where it's missing. So the annotation has to tell me how to get the missing pieces. The how is important, not what the missing pieces are. If I just tell you what the missing pieces are, that's useless. You have to tell you how to get, you have to know also where to use what. Well, but that's just a program, isn't it? That should be just some piece of code which I run whenever I have a question. How do I know that these two things are different? Well, the answer, that these two things are equal. The answer is, well, you run some program which convinces you that that's the case. That's the witness. So I'm going to say the witness is a piece of code. So the annotation is the witness, is code, which computes the witness. For example, a trivial piece of code would be code which immediately returns this witness Q. And then I have it. But maybe it's code which is more general. Maybe it's code which gets run in many different situations and produces the missing piece according to what the situation is. It could be a piece of code, for example, which performs one of the steps in the type-directed algorithm. It could be something that says, oh, let me check against the type. Oh, the type here is a product. Let's try first and second projections. So these could be little algorithms that help me build equality proofs. So in general, I'm going to have the following idea. The input to a proof assistant. I'm calling a thing proof assistant, but what I really have in mind is some sort of any kind of algorithm for checking that things fit. So this might be just more like a checker that is checking whether formal proofs are okay. It's a program. It's a computation. It's not a raw term. It never is a raw term. Right? If you think about it, even Agda, which pretends to be very pure, right? When whatever the user types in, it's never a proof term. It never is. At the very least, you have to check that what he typed in makes sense. So even if he types in just nat, you still have to look and say, oh yeah, that's a type. Right? If he types in something like s of 0, it sort of looks like a type term, like it looks like a proof term. But you have to do something with it before you know that it's a proof term. You have to at least scan it and make sure that it's okay. So I would prefer to think, I'm not going to think that a proof assistant accepts a term and a type and tells me whether everything is okay. Because that's not what happens. A proof assistant accepts a piece of syntax, then it has to do many things with the piece of syntax before it arrives at the judgment. Okay? So naive view, let me call it naive. Naive is the input to a proof assistant is a judgment. And the output is either okay or not okay. You give it a judgment, and then it tells you whether this judgment is derivable or not derivable. That would be a naive way of thinking about what AGDA does or what COG does. But that's not what it does. It never does that, because the real input is never a complete term. It's always got, in most cases, it has missing information. In fact, you rarely provide A. So typically what you have is gamma, and you have a piece of A. You don't even have a whole A. Here you have A with missing info. Because you did not provide implicit arguments. So at least the implicit arguments are missing. In COG, it's even worse. In COG, the information that's missing might be something that you calculate through the type class resolution, which is an arbitrary prolog program. So the stuff that you have to generate before you even find out what A was is substantial, right? So this will only lead you through a lot of computation to the actual A, and after that you will try to calculate the type. And then you will tell the user, yes, it's okay. But what's the thing that's okay? Well, yes, it is the case that the little a has the type big A. In most cases, the user will never see the little a. The user doesn't want to see the little a. In COG, you set printing all, and you look at what you actually proved, and you can't tell what you proved because the terms are huge. So already the statement of the theorem typically will be such that you want to see the abbreviated form, and you don't want to see all the explicit arguments everywhere. So I think a more realistic view is that what the proof assistant accepts is not directly the term that you're trying to check. It's something that comes before the term, and in that case I can say, well, it's a computation, and this computation, when I run it, will give me the judgment. And then I may actually find out what judgment it was, but I hope to write code which doesn't trick me. In fact, in COG you can write code where you state a theorem and it looks like you are proving a theorem, but in fact you're proving something completely different. First of all, you can use notation to trick people. But then you can also use class resolution so that nowhere in the input can you tell that it's going to go off into some type class resolution and do something weird that just doesn't make a lot of sense. Yes? So you shouldn't write code like that, but you can. Okay, so we're going to view things as programs or as computations, and then when you run them, they do something. So then that means when you have an input, is a computation, C, we need an evaluation strategy, and what you get out is a result, let me call it value, and this value, well, presumably a full-fledged type proof assistant can produce things like integers and strings and so on, but the pure version of it would be that the value is a judgment. So it has now computed the fact that we have some sort of a judgment. How many is judgment? Okay. Here, this calls for an operational semantics of what's going to go on here. You want to say what's going to go on. So questions. one. What's the evaluation strategy? Another question is there a static semantics to this? Do we want to do some before, as a good programming practice, when a programmer writes a piece of code, you may want to type check it before you run it, because that turns out to be a useful debugging tool. So maybe we want static semantics. So this would be some sort of type checking or something like that. Okay, so those are the things we want. Now, first of all, forget about at least full-fledged static semantics. Well, maybe a little bit. You can hope to have a little bit. But because we're going to be calculating the dependent type theory, the distinction between evaluation and type checking is not really meaningful. In order to type check a program, a dependently typed program, you may have to perform an arbitrary amount of computation. So there may be some sort of a top layer of type checking which is very crude, but it certainly wouldn't guarantee that everything is going to go okay, because in order to guarantee that the program will not go wrong, a dependently typed program will not go wrong, in order to guarantee that, it's just as complicated as running the program. So you can't do that. So maybe a little bit. And now then there's the operational semantics. How is this stuff going to run? And here, I would like to explore the view that maybe we can use the ideas of handlers and computational effects. So effects. Now I have told you exactly what my hammer looks like. It looks like effects and handlers. Okay, so everything. It may not be the correct way to do it, and I'm willing to consider the fact that this is completely mistaken, but I would prefer to be faced with positive evidence, not negative evidence. So if this is completely wrong, then I would like to hear what's a better way to do it. The idea would be the following. In general, think of. So now, oh, by the way, so now I'm not going to think of a computation as a derivation anymore. Instead, I will think of a computation as an evaluation. So I have a C, which will evaluate to some result. So at the end, I hope to get a judgment out. And so now I have a derivation here. At some point, so I have a what is this? The evaluation tree. So it's a tree which tells me how stuff got computed. Somewhere in the tree, I will be faced with a question such as, why are these two things? You have to check that these two things are equal. So I will still be faced with the task of checking the two things are equal. And in general, whenever I get to something that I would say is a proof-irrelevant operation, so something where I don't have to record what happened, maybe also when I have proof-relevant operations, but definitely for the proof-irrelevant ones, I would think of these as operations. So whenever I need to check that two things are equal, that for me would be an algebraic operation saying, and now we're going to calculate a term of type xy. So an operation returning something of this type. This would then run some control mechanisms, such as the handlers. Handlers are a fancy control mechanism, but maybe it's not handlers exactly the way they are usually thought of, which will interpret the operation to do the appropriate thing that will help us generate this egg. We would imagine that the C here may contain further control mechanisms, so handlers, which tell us how to do this in a particular situation at hand. Right? So I first run my C without any handlers. It gets stuck because it doesn't know how to do this equality thing. And then I say, oh, but I know how to do this equality here because I have an assumption and I could just tell the computer that it has to use that assumption. So I would install a handler which says, and by the way, when you get to this situation, you can use that particular assumption and you will be done. And that's a hint. And it tells me how to do things. It tells me when you get to this operation, and if your argument matches such and such form, then you can use this handler, and then you will be done. Okay? So that's the idea. I want to invert the control so that the operational semantics sort of jumps out of whatever it's doing when it gets to the tricky bits. The tricky bits are handled by outside handlers, and then it resumes wherever it left off. That's the grand plan of what we're trying to do. Okay, so I would just like to address one other issue here. So now, of course, everything is here open. Do we use handlers? Do we use F-style handlers? Do we use a different kind of handlers? In addition, maybe we don't want to use handlers. Maybe we want to make it look more like Prolog. There's lots of questions there. What are some of the goals? I would like to use this mechanism not just for equality proofs, but maybe also to calculate implicit arguments. So I would like to have a base language which is sufficiently expressive so that I can implement on top of this language the usual common algorithms that show up in proof assistance. So we want the first question is, we want a base language which is expressive enough to do what? Well, one, I want to be able to manipulate equality. But by which I mean, I want to be able to do something about missing equality proofs. But I also have an opinion about what sorts of equality proofs I need to worry about. I don't care if somebody assumes D equals D arrow D. Frankly, it's not my problem. Okay? So I want to be able to help people who want to introduce new type constructors with new computation rules. For example, maybe my proof assistant doesn't have products. And then you can axiomatize products. And when you axiomatize products, you also axiomatize the beta and eta rules for the products. It should be very simple, and it should be easy to add these kinds of good betas and etas to the algorithm. It should be easy to install handlers for new betas and etas. Should it be easy to handle a non-normalizing term that somebody produced because they assume that D equals D arrow D? No, I don't think that. I don't care whether that's difficult or easy. If they want to do it, they can try to do it, but I'm not going to worry about it. So when I say manipulate equality, I mostly have, what I have in mind is add new beta eta rules. So this is why I was mentioning at the beginning that this is going to look a lot like LF. It's really going to be something that's it's a meta level, because it would let people experiment with new beta eta rules. I remember when we were first doing homotopy type theory, it was really, we would have been very, very, very happy if at that point there was a way to add new beta rules to Coq, or new beta rules to Agda. And then Dan Licata came with the trick to add beta rules for point constructors for high inductive types. And that essentially was sufficient to lure several young people from Coq to Agda, and they produce proofs in Agda ever since. So this is very useful for experimenting. So manipulate equality. But also this base language should allow me to, without too much pain, to do things like calculate implicit arguments. I don't think the implicit argument should be part of the kernel. There should be a core kernel, which is very small and very dumb. And the kernel, the dumb kernel, the evaluation strategy, should be dumb, and whenever it says, I don't know how to do this, that's an operation. And then somebody else has to do it. Well, you can now go down the list, right? So once you say, well, I could calculate implicit arguments, then you could say, well, I could also implement type classes. Or if you want canonical structures. these are all techniques from existing proof assistants, which are hardwired into the proof assistants. And then you need to go to Paris and then talk to people if you want to get modifications. Right? And then they hack things, and then they produce the next version of Coq, and then it's much better than it was. But maybe I do not really think of the whole thing as something that is going to take over the world of proof assistants. I want this to think of it as an experimental tool, a tool where you can experiment with a new technique, and then maybe you can just sort of make it up on the fly. So if I can get all of this, that's of course excellent, right? I think it's very ambitious. We'll see how far we get, but this is the sort of thing we're thinking of. Now, for the last bit here, there is really no talk about the reflection rule. No, you could do a lot of this without the reflection rule, right? So where does the reflection rule come in? First of all, I don't think it necessarily comes in. I think a lot of this could be done without the reflection rule, but if it is done without the reflection rule, then there is going to be a complication, namely that we will have to deal with different kinds of judgments. Then we will have to be able to speak about equality as a judgment and constructing a term as a judgment. So what the reflection rule is doing, it's simplifying. Reflection allows me to present everything with a single judgment, with a single kind of judgment. Sort. Right? Whenever I want to say, why is A equal to B at type A, I can say instead, well, can you please inhabit this type? So it seems like, if you now think about what will be the basic concepts, the basic concepts might be, and maybe not all of them, might be, check that A has type A. Infer the type of A. Inhabit a type. Where the basic usage would be inhabit an equality type, but once you start thinking about how to inhabit an equality type, you quickly get to recursive calls which say how to inhabit a general type. So you might as well say something like that. Okay, so maybe these are the sort of things that will be basic building blocks. And then the kernel never has to say, prove this equality for me. Because that would really entail a whole different sublanguage for dealing with equality. So I think this reflection rule is more it's kind of a simplifying. At the same time, it's complicated, but it's also a bit of a simplifying thing because there are fewer things floating around. So that's, I don't know if that's, maybe in the end we will say, well, we don't need the reflection rule. I don't know.
Little bit simple, but very complicated.
Yeah, something. Yeah, I don't know. Well, we'll see. Yes. Okay. So let me finish with some benchmarks. What would be the benchmarks here? When do we declare victory? What sort of things do we need to do to declare victory? Okay, so one would be a benchmark for expressivity to be able to define new type constructors with their new computation rules. With new computation rules. For instance, it should be possible to define the higher inductive type circle in this system with the desired computation rules. I should be able to tell the system what the beta and eta rules are. And then there should be a reasonable way of using these rules. So preferably as automatic as all the other beta eta rules that are already there. That's a good, so type constructors, so what would this be? This would be things like, maybe I want to define products, competition products, so sums, maybe, I want to be able to define sigma as a derived concept, or the circle, the higher inductive type, or I want to be able to define an inductive type such as the natural numbers, and it has to have the correct computational behavior. So I don't want to do everything by hand, it just has to use the betas and etas. So that's one kind of benchmark that I'm after. So another benchmark would be to do something that is hard to do in intentional type theory, because this is going to be extensional type theory in the sense that you have extensional equality. So maybe one such thing would be to define, construct, here's one from the hot community, semi-simplicial types. So essentially this means that I want to be able to reason about a certain category of presheaves. And it's nasty to with only intentional type theory. Nobody has managed to say exactly what's going on, but it is widely believed that you can do this if you have good enough equality, so strict enough equality, and it should be possible to do it. So another one related to this one is it should be possible to define or express something like Voevodsky's HTS type system. So what is HTS? HTS, it has two equalities. It has a strict equality with the reflection rule. Well, that would be our equality. That's our ek. But then it also has intentional equality. Let me call it path equality, which would be maybe written as path. And this is more like Martin Löw's identity type. But now, if you're not careful about how you do this, then you will be able to prove that the two are equivalent and that this one is trivial, okay? But this one is only for fibered types. So there is a notion in this type theory of a type being fibered or not, and then you can only do this for fibered types. So it's an additional thing. So for example, so actually you should try to do step 3 before you try to do step 2, because step 3, is that true? Step 2 should give you a model of 3 or something like that. So there's some relation here that okay, so these two are not entirely unrelated. So this would be more like, it's a good experimental rule. It's a good rule. It's a good system for experimenting. Whereas this is, can we do something new here? Okay, so that's the sort of thing we're thinking about. I can stop recording and then you ask questions, or you can ask questions and then I stop recording. Or you can just go away. Stop recording. Okay.